Hello, today I would like to tell about the paper called On Linear Sets of Symmetric Elements, which wrote the base paper award on CLAM 2020. There is this certain set of problems when the input data is represented as unordered set. For example, if you want to deblur the image by using a set of noisy images or of the same scene, or if you want to reconstruct the original order of sequences of frames for video or point clouds and meshes. And this way we don't care about the order of samples in the set, and we would like to make sure that this prior is not incorporated into the model. The major contributions of this paper are follows. Authors formulated the problem of limited expressive power of deep sets architectures. They proposed a model architecture called deep symmetric sets, or DSS, both invariant and equivariant to the order and translation of input samples. They mathematically proved the proposed method model architecture, and they provided benchmarks for a variety set of tasks and various data types. There are two major properties I would like to point out about deep sets. Ideally, we want to learn a neural network which is insensitive to the order of input samples. When applied when, for example, applying the shuffle on the set, it returns basically the same result. This is called the translation invariance. In addition to that, we want to learn the neural networks, such as shifting the set of original images also return the shifted result, which is also called as translation equivariance. Deep sets, it is the prior work of this paper. The major disadvantage of this model is summarized in a lack of information sharing between channels in the model, which limits the explicit power. In this paper, it also denoted the late aggregation. Previous works also attempted to incorporate information sharing layers, but it was not so explicit. So how can we create the model architecture such that it both translation invariant and equivariant without loss of expressive power, and do it computationally efficiently? Before moving forward, I'd like to introduce you to some general notation of the paper. Authors call H equivariant or invariant networks as networks that purposes along with the general dataset. Also, they call G equivariant or invariant networks as an extension of H networks if their properties correspond to all possible permutations of deep sets. It is clearly to see that G networks needs much more explicit power compared to H networks. They introduce the model called deep sets of symmetric elements, or deep sets. Same to deep sets, each sample is fit into the independent scene and channel L1 with shared weights. However, it also includes an additional layer L2 that gets the input the sum of all input samples, and the output of L2 is summed up with the each output of L1 independently. After that, resulting feature representations of L1 are concatenated together for providing the output prediction. Authors characterize the model architecture by two theorems. The first one says that any linear G equivariant layer is the form of some input samples bypassed by L1 and L2 linear equivariant functions. And if you can see that this theorem is directly reflected in the model architecture. X1 over here, this is input of the model, which is the samples in the deep set. L2, this is the convolution layer, which gets at the input the sum of input samples. L1, it is the shared layer, shared convolution layer, which gets each sample independently. And summing up or early aggregation is introduced by the sum between L1 and L2. The general intuition of the theorem is as follows. The sum of linear equivariant functions are equivariant. G equivariance requires more explicit power of the model by and by incorporating additional L2, this layer into the network, it increases the explicit power by at least a factor of 2. The second theorem is an extension of the first one at some point, and saying that sharing information between L1 inputs synchronizes independent H equivalent outputs into the global GH equivalent representations, which is basically means that L2 incorporates global features into the local feature obtained from each of L1 channels. The proposed architecture provided in theorem 1 is compared with original deep sets, which is denoted as the late aggregation networks, and as well as aggregation methods proposed in previous papers. As the evidence of efficiency of the proposed method offers tested DSS on a diverse set of data types, such as 1D signals, images, point clouds, and meshes. The objective of the first task is the classification of 1D signal measured multiple times. So that's basically the same signal, but with applied different augmentations and distortions, such as noise, random amplitude, baseline drift, and frequency shift. The objective of this task is to classify the shape estimated by accuracy. As you can see on this diagram, the proposed aggregation method significantly overperformed competing methods. Another task was understanding interframe relationships. For the point cloud and meshes task approached on the false dataset, it was needed to predict what frame was in the middle along with others. For another task for video network was learning what frame was the first along with others, and both tasks are estimated by accuracy measure. As you can see, all early aggregation methods beat baseline. However, aggregating methods from the previous work demonstrated better scores compared to the sum aggregation proposed in theorem 1. This could be related to the non-Euclidean and non-linear structure of the point clouds and meshes, which is out of the assumption in theorem 1 about linearity of L1 and L2. For another task, the deep neural net was learning the selection of the image with the best image quality. The dataset forms as follows, and the set of occlusions and Gaussian blur was applied on the original image. The metric of this experiment again the accuracy. And as you can see on this slide, the proposed method overperformed others on the Gaussian blur task. On occlusion task, when the transform is a bit more nonlinear, the method overperformed baseline. However, different other aggregation methods overperformed the proposed method. For this experiment, the neural network was trained in constructing the order of RGB channels after shuffle. So basically that's authors claiming that for this task aggregation is critically important. And finally, for the last experiment, the neural network for reconstructing the original image from the set of blurred images. For both of these tasks, the optimization objective was mean square error metric. As you can see, the proposed method significantly performed the baseline, but the aggregation method proposed by Ital shown the best performance along others. As the recap of results or experimental results, the proposed method as max or sum aggregation works well on all tasks, which makes it more universal compared to the earlier proposed methods. Aggregation method significantly performed deep sets on the point clouds and mesh data types, which probably could be related to the incorporation of the global features into local representations. DSS aggregation methods provided by Sridhar works and Italo aggregation techniques may fail on several tasks. There is some critique for this paper. First of all, this is the assumption that L and 2 layers of the deep symmetric sets network are linear, which is completely not true, just because we have nonlinear activations along these convolution layers. And based on the first critique, G covariance is relying on the same position of the objects on all images and samples, which means that if you have some shift between the camera position, let's say of the scene on the image, or camera position of the scene of the point cloud or meshes, the result could be even worse. Also, the proposed method haven't shown the solid consistency in experiments. As the recap of contributions, authors formulated the problem of limited expressive power of deep sets architectures. They proposed their own architecture called DSS, both invariant and covariant to the order and translation of input samples. They mathematically proved the proposed method model architecture, and finally they provided benchmarks on a variety of sets of tasks and various data types. Thank you for your attention.